Right, my name is Raphael reminded you was David Simkin. I'm part of the Warwick Manufacturing Group, part of Warwick University. So my talk today is going to be innovations in coil windings. Now that isn't quite as dull as it might sound. In fact, to me it's remarkably interesting, so you'll have to be careful I don't go over the 20 minutes I've been given. The thing is, one of the reasons I'm here, and I'd like to thank Geraint for giving me the opportunity, is we were fortunate enough with applying for a DER grant to create a winding centre of excellence at Warwick University. And so we made the case that, as it says here, it's a need for UK industry, not a want. One of the things quite often, we do big picture stuff where we look at big picture things, but quite often, and when you're a small company starting off, you need access to certain things that you need large capital items for, which the government has given that capability for us to get, which then allows the SMEs and larger companies too to access. So we've been fortunate enough to do that. So yet again, thanks go to Catapult and DER, who funded us for in total £4 million to create that the winding centre at Warwick. Right, so so that you know how we're going through the so that you know how we're going through the route. So I'm going to go through why there's a need. Although I'll go minutiae of windings, it's really important that you always consider the holistic approach. So an e-machine does not sit alone in that structure. It's part of a big system that goes behind it. So I'll show you why there's a need for innovations in winding, and it doesn't really relate to the e-machine, really. So then go through, I'm not sure how great a knowledge there is on winding capabilities, so I'm going to go through discrete hairpin, which is where automotive are at the moment, and wonderful things you can do with a needle winder, which hopefully by the time you finish, by the time I finish, you'll understand. And then concentrated wound, which is a big thing for aerospace. And then topologies and new materials. Things were mentioned earlier about aluminium, and someone said materials aren't changing. Well, I can tell you we're working with aluminium with nanoparticles on the outside to make it different for winding. One of the things you find with the 1000 series superconductive aluminium, or superconductive for aluminium, is that they're very difficult to wind because they're very ductile. However, if you start doing things like putting nanomaterials in the surface, you can change those material properties for winding. So there's lots of things you can do with materials now with all the concepts that have come recently. Whoops. Right, so why is there a need for innovation in winding? Well, my background recently, over the past 10 years, have been things to do with traction. So things to do with Koenigsegg Regeras, so very posh sports cars, Formula E, to more recently BMW Jaguar Land Rover automotive traction. Now, the issue there, I've been working with electrical machines one way and another now for nearly 40 years. And when I went to BMW to meet their head of production there, he said to me that I knew nothing about making an electrical machine. And I took that really badly at the time. I was not impressed. But in fact, he was absolutely 100% right. I did not know about making e-machines for automotive traction because it's entirely different to what I've done before. It's important that you take all the words in that sentence in their way. It's volume production of technically advanced electrical machines. Before, up to now, I'd done technically advanced e-machines. I've made 10 of them. I've made possibly 100. Volume production is very different. One of the reasons the winding centre exists is that I've got a production line that runs off 1,000 units a day. As an engineer, even though it doesn't matter how high up the line you are, you cannot get time on that machine to play around and do little tests. What happens if I make this twist, or I do this, or you haven't got time? That machine runs 24/7. So that's yet again one of the advantages of the winding centre. It is a similar to production machine that you might have in Dingolfing in BMW that you could play around with and try. So that's one of the reasons hopefully the JLRs and Fords will use it. So why have I put that large graph up there with pictures of batteries? One of the reasons that automotive want to move into electrification is that they'll be fined very heavily if they don't. If they don't reduce emissions, they will be fined for each vehicle they sell. So if you look at the little picture that you see at the background, you can see the electric vehicles is where it's at, fully electric vehicles. Because if they don't make fully electric vehicles and get us all to buy them by certain points, they will be charged for each car they sell. The other ones get them to lower emission, to reduce emissions, but not sufficiently quickly, which is why I have Tesla who buy emissions from Fiat until recently. So, Fiat who buy emissions from Tesla until recently. So if you look at that, you'll see that the battery cost is huge in relation to all the other costs of the system. So you might say, well, why am I worrying about winding EV machines? Surely I want to do more and more work on the battery. The reason for that is a small saving in the efficiency of the battery, or really let's consider it an electrical powertrain, is going to reduce that battery cost quite hugely. So really it's well worth putting a lot of money into saving 2 or 3% efficiency in the system through the e-machine, because that saves you quite a lot of money on the batteries. So that's why. And if you look at it, one of the things that's happened in the past is that a lot of my life has been spent with working with round wire. That doesn't have a very high packing factor, whereas now there's a big push, certainly for automotive, to do rectangular wire. Lots of work now with rectangular wire, much higher packing factors than you might have normally. So this is how a discrete hairpin's made. I'm very much a manufacturing person now, not a design person. So a lot of the processes are similar that you would have seen in a standard manufacture of a wiper blade motor or something. So you have slot liners, you're going to have some sort of impregnation station at the end, you're going to make your connections to the outside world. There are lots of bits which are different though with a hairpin. You have to make these individual discrete little hairpin forms. You then have to insert them, which is what's being shown manually here, into the stator. That's done robotically. Then you have to twist them at the other end to make them all connect up. And that has to be done very accurately, because the next process is going to be the laser welding. So that twisting process is probably one of the more technical bits in all that process, which until you actually think you start doing it for real, you don't realise. Because if the wires aren't close enough, the laser welder won't weld them. There's a vision system that says, I won't weld. So all told, discrete hairpins have their place. There's a challenge with repeatability because of that weld joint. Sometimes they don't weld. The vision system looks at the shape of the weld, whether it, the concaveness of the weld to assess whether it's good or not. But there's a lot of work that goes into that, and not always perfect. So this should show you now the components of a winding machine. I'm not sure how many people in here know a lot about winding. I hear we're going to see one later, which is great. So this is a winding machine that we're going to have at Warwick. So winding machines have a bit where you have the coil. It comes off the coil. You're then going to have it all straightened in these straightening parts. And fed through. There'll be a belt system here. This belt system is very simple. All that's going to do is use friction to drag the parts through. There's then a stripping section that can either be done with a grinding process, CNC, or else lasers. Quite often it's used as a grinding process nowadays, just because lasers have a high capital cost. It's then grabbed through. There's an area where it's kept sort of fallow to get ready before, just in case if something goes wrong, you can cure the problem before it goes into the machine. And then it's grabbed into the machine, straightened again with these straighteners, and then rotated through. The particular unit we're getting is not considered production ready. You're about to see the number of parts that come off. This can produce about 1 part a second. This is not sufficient rate for most production plants. Automotive, where it's about half a second and better. We like this route because it allows us to form a shape that we want. So this is programmable. One of the challenges with the other method, which is you form a 2D shape and then press it into a 3D form, is that press tool is made based on what that copper is that you received. The challenge is normally that the copper you receive is different spool to spool. Its mechanical properties can be slightly different. And so the bends can be slightly different. So one of the challenges is if you've made a press tool that is based on a certain ductility of the copper, if the next one isn't quite the same, then the shapes don't come out the same because it springs back. The spring back is different. This allows you to control that. And also it allows us to do hopefully some things with Bristol where we can wind some coils for them, some flat coils. This can wind axial flux coils, for instance. I'll show that later. So that's, you might say, is old hat, because that's the sort of thing I saw in Dingolfing 3 or 4 years ago. So what's the future for winding? Because that's where we're here, innovation for windings. So what's known as continuous hairpin. And now it's a totally different process. In this case, what you're doing is this big spear that goes through the system, and you use a needle winder to wind wire onto the spear. This is complicated to the extent of design. You have to think before you design the system how this is going to work when you start inserting it in. Whereas the previous one, you could get away with a twisting station at the end. In this case, it has to be designed as if it were a continuous hairpin. The big advantage here is that you don't have so many welds. So instead of at least 200 welds in most cases, the Ford machine now has over 200 wells. It goes down to a little over 10, which is great for reliability. Also, you don't have the possible failure of this gets put into a fluidized bed to coat the ends. So all told, this is a much better route. Also has lower resistances because you can do things. There's a bit of a process involved with it though, because once you've got the mat, you're now going to have to insert that into the stator. So imagine your little teeth you had before that you put down in, you can't do that. The slots have to be absolutely parallel so that the wires can be pushed from the inside. So what you do is you push the mat that you've got into a sort of jig system, and then that jig system is taken to the stator, and those wires are then pushed out into the slots in the stator. So quite a bit of a process, but it gains you quite a lot. So for the automotive companies at the moment, most of them are either working on this or have already completed working on this. One of the challenges with this process is it's actually patented by one of 3 or 4 companies. So, Ford, for instance, don't own the rights for this. It's various winding companies in Germany. Right, you can see this is my particular hobby horse because there's lots of. When I started the Advantages, I had 2 or 3, and then it went and it grew and it grew. So one of the challenges with distributed windings, they're used in almost every electrical motor that we have, is that the fill factor is pretty low. Also, if you're going to manufacture with it, it's pretty bad hand winding if you've ever tried it, but it's pretty bad in production. The challenge being that the machine itself to do that is very bespoke, to do the one task that you've given it to wind a particular machine, and also costs about £1.5 million for each one because of that bespokeness. You can see videos online where they do the insert method. You have lots of coils and they get inserted and pulled down into the slot. They can get damaged as they get pulled in due to the fact that all the wires are crossed over when you see them. It's pretty obvious when you look. The needle winder, though, has the advantage that it can put wires really where you want them to go. One of the things as a designer, you put it into your wonderful CAD package and they go coil here, coil here, coil here, coil here, coil here, coil here, coil. And when you start looking at where the wires actually go, which we've done via some CAT scans, CT scans of wound electrical machines, they go all over the place. The needle winder helps with that to try and get the wires where you expect them to be. They also give you more strength. The big downside for these is that you're going to have problems with speed. For us, for the winding centre, that's not a big issue for us because we're what I know as X-build, so experimental build or low numbers. So it's not a problem for us, but can be in production. But for a lot of the companies we hope to deal with, that shouldn't be a problem because they, SMEs, for instance, only want to produce possibly 100 machines. So this is how the thing works. One of the other challenges with the distributed wound motor is the end windings, which can get a bit of a heap. Whereas in this case, you'll see as it winds through, the reason it's got these little spokes on the outside is to try and make sure those end windings don't grow to the outside to make a long electrical machine, which can be a problem with the distributed wound system. This is slowed down a bit, so you can see how the process works, but not massively. So this is sort of the speed it will take. Another advantage with this is that you can do lots and lots of parallel wires. We can do 24 parallel wires if we wanted to, which would be interesting in a standard insert winder. But you can see for the speed would be prohibitive for most production routes. Running to the end now, so this is the concentrated wound. You can do the same thing with concentrated windings. You wouldn't notice unless you consider production. One of the really important things for production is that you want everything automated. You want the winding automated and you want the joining automated. One of the challenges with some of the spindle winders, which is where what happens is, I don't know if that's what we'll see later on, Garai can show us, where the wire, a thing rotates and the wire goes onto it, is what happens with, where's this tail, which I then have to bend into position for then something else to weld. One of the nice things about the needle winder is it can take the tail to where you want it to be, which then means that when you then weld it later on, that welding robot knows where the wire is going to be because it should be there, as opposed to having to have some manual intervention. So yet again, the needle winder helps with that. It's as quick as the normal system, but it does give you that better control over tails. And lastly now, one of the challenges often happens is if you look at things to do with, I used to work for a company called Yasser, axial flux coils. You don't want those coils to build up in the center, which they would do if when you bend it. The machine I just showed you, the robot bender, is able to take all that into account. Yasser have just bought the same machine we've got, for instance, so it shows it's valuable. Also, if you need to consider new conductors with windings, so we're doing work with on various projects to look at aluminium. There are things you can do to put a coating on the outside, perhaps. It has advantages of low cost and low density. I've put the picture of an aircraft up because it's seen as a possibility for aircraft, not due to the low cost, clearly, but mainly due to low density. And oddly enough, it's a surprising thing when you think about it. It has actually got lower CO2 emissions. And you wonder why. The reason is that if you think about it, most of it is done because it's such a high energy intensive process. It's done in areas where there's hydroelectric. So hence CO2 emissions, oddly enough, are lower for aluminium than copper. And then you get to the final bit, which are things to do with thermoplastic insulators, things to do with peak, where there's a big move now to 800 volt systems for lots of things, for aerospace, 1200 volts, but for automotive 800 volts, because we don't like to wait for 5 hours for our cars to charge, we want 20 minutes, and so there's a push for that. And yet again, the higher temperatures, all of these things, which means that you need to look at things beyond enamel. Right, thank you very much. Thank you.